Okay. Okay, so if, okay, annotate, I like to annotate. So today we are going to start by, excuse me, I hope you all can hear me clearly. I'm sorry, I had a little bit of a rough throat this morning. Hope it's not the virus, but we'll wait and see. Okay, so slideshow. Okay, now this is something I want you guys to have an understanding of, okay? And I'm not saying that, but I would like you to have an understanding that this is straight out of a textbook, you know. Okay, first of all, you all know that, I mean, you all know that when a beam, okay, when a beam is being subjected to some kind of a bending stress, in other words, if it's loaded here, we know that this is the neutral axis, and we know that we have compression here if it's simply supported, that is, okay? We have compression there and we have tension here, okay? Now, steel is a great material as long as you keep it in tension. When you start putting it in compression, it's going to have a tendency to buckle, and therefore it's going to fail before it can actually reach its ultimate strength, okay? So here what they're trying to show you is that these are the compression forces or compression stresses, okay, that are in the top flange. And of course, this, your neutral axis is here, okay? And as the compression region of a beam is subjected to increasing stresses as the external load increases, in other words, that makes sense. The stresses, you know, increase in proportion to the load. In other words, because as long as you stay in the elastic region, it is possible that at some level of stress, that the yield strength of the plate elements, the flange and the web that make up the cross section will buckle out of plane. Okay, so the nice thing about steel is that they were able to, you know, keep on increasing the strength, keep on increasing the strength. In other words, we went from, I think it was 260 MPa to 300 MPa. Now we're working with 350 MPa. Okay, so as the steel got stronger and stronger and stronger, well, they were able to make these, this is what they mean by the plate element. In other words, this is like considered a plate element of the flange. This is considered the plate element of the web. Okay, so what happens is that if this is subjected to a compressing force, okay, it's just like a column. If that element is too long, okay, it will buckle, okay, prior to reaching its maximum strength. So what they found was is that in order to be able to design the resistance of this element, okay, they started classifying the different sections. They just started putting the steel into a different, like class 1, class 2, class 3, class 4, and so on, okay? And of course, depending on in which class these elements would fall under, okay, then, excuse me, the steel would behave a certain way and will be able to reach a certain level of resistance. So that's what they're saying here, okay? Now, of course, it can be either the flange, you know, that buckles, you know, warps and buckles, or it can actually be the web. It doesn't matter. So you have to check both. So if this happens, attempts at increasing the load simply results in magnification of the buckling, and further deformation produces a rapid reduction in the moment capacity. So instead of the thing actually going up to its yield strength, the thing will buckle and will fail. That's what they're basically saying. Now, so what they've done in steel, now you see here, I want you to know, I have it also on the next slide, but so the approach that is used in steel is to establish limits of tenderness for any elements that are in compression, such as the desired overall behavior can be attained. So they've come up, of course, you know, experimentation, calculations, all that. And then they came up with this table, okay? So this table here tells you that okay, so what this table, so these are the different elements, okay? So in other words, flanges of eyes, okay, flanges of I sections, and of course, I sections is also a W section. You understand? They talk about I sections and T sections, okay? plates, okay, and then these are stems of the T's and flanges of rectangular hollow sections. Those are the HSSs, box sections. In other words, if you make a box section, you build up a box section. This is the webs of your HSSs, and then of course this is for circular HSSs. So these are the basically covers the geometry of most of the plate elements that we would use in our steel design. And what they're saying here is that if you take the value of BEL, okay, which is basically the width, this here, like I said, in steel, this is always called B and this is always called D, okay? So if you take in other words, if you take half this width here, okay, in other words, what they call here BL, and divided by this thickness here, if that ratio happens to be less than this constant divided by the square root of the strength of your steel, then you're in a class 1, okay? And of course, if all of a sudden you want to see if you're in a class 2, well, you take the same ratio of that and you divide it by 170, still okay. And if you want to see it's a class 3, then of course you divide F 200, okay? So this is how you test, okay, whether you are in a class 1, class 2, or class 3, okay? Now, so this is for the flanges, this is for the webs. Now here, this part is if you, for example, have also a compression force in your member, which is sometimes very unlikely for a beam. Okay, this applies more for a column. Okay, so therefore, all you have to worry about is this ratio here because the CF value in your beam is 0. This is not the CF of the bending stress. This is the actual force. So if you do have an axial force, you have to worry about this. Otherwise, you just worry about this part here and so on. So you can either remember, or what you should do is you should just determine whatever shape you are planning to use, okay? If you want to calculate the resistance or use the resistance of that shape, you should make sure that it falls under either class 1, class 2, class 3, and you can even have class 4. Class 4 becomes very, very flimsy steel. And then if ever you get into class 4, the standard that you like, everything that we're doing here is done by the CSA standard. Okay, everything that we do for building structures is CSA S 16.1. And if ever you happen to fall in a class 4 here, okay, you would have to go to CSA S, I think it was 36. I think that's what it is. Anyways, I've got the standard. Just okay. So this table here, okay, I will show you where I use this table here later on when we're going to be doing our project. So you'll be able to refer to it. You'll see this in one of the labs. I will come back to this table. But instead of worrying about this table, if you guys ever buy the handbook, okay, if you ever buy the handbook, then in the handbook, they have tables. Okay, so they have tables already prepared. So therefore, once you pick a section, for example, okay, this is all welded white flange, use very little. Okay, so for example, if I happen to decide to use a W 310 by 79, okay, W 310 by 79, well, that happens to be a class 2. Okay, so this table already has done all those calculations for you. So you can quickly check from this table. Okay, so that's another thing you can do. You can come to this table, and I sent you this table with the lecture this morning, so you have this table. But if ever you need to go, so you have this table here. Otherwise, you can forget about this whole thing and simply use the beam selection table. Okay, so okay, just before we get there, okay, now if you happen to be falling into a class 1 or class 2, okay, this is how you calculate MR. Okay, first of all, what class 1, class 2 means is that the elements will not buckle, okay, and the whole thing can plastify. Okay, so in other words, this can actually plastify. In other words, the whole section can actually yield before it actually fails. And when the whole section can plastify before it fails, that's called the okay? So here's how you calculate MR. MR is equal to phi Z Fy. And what is MR? Is a factor moment resistance. And phi, of course, is 0.9 for structural steel, as opposed to 0.8 for 8.5 for reinforcing steel. And Z is the plastic section modulus. Okay, so this is what Z is. Okay, it's very similar to the other section modulus, the elastic section modulus. But that's the significant difference, is that if the thing will not buckle, okay, the whole section can plastify, and therefore you can calculate the resistance based on the plastic section. And that's what this is. Now, for a class, and then of course, Fy is the yield strength of the steel, and we're always going to be using 350 because that's what's produced right now. Or as a matter of fact, we'll use 345, and I'll explain that later on. Now, for a class 3, the difference is that this is what happens, okay? Only the top will start plastifying, and then all of a sudden it will buckle. So in other words, here what happens is that MR is equal to phi. Now, instead of using the plastic section, you use the elastic section, and that's what you guys have been, you've been used to so far when you calculate the section modulus. So MR is equal to the factor moment resistance, and then of course this is the same thing. And here, of course, this is the elastic section modulus. So this is plastic. That means the whole thing will yield before it fails, and then this upper part here will start to yield, and then most likely will buckle. Okay. So that's the difference in for when you have a class 1 and a class 2. And people say, well, what's the difference between a class 1 and a class 2 if you use the same thing? Well, this one here, class 1, would be guaranteed to develop a plastic moment. So you use class 1s when you're designing for earthquake reasons. Okay. And then for resistance, it makes no difference whether you use a class 1 or a class 2. So as long as, and that's why when you're checking the section, if you check for the class 2 requirements, which is less severe, and it happens to be a class 1, you don't care. It's going to be good. You can always use this equation here. So these are the equations, okay? So if ever you want to calculate these things from scratch, then you can actually take this, the reduction factor 0.9. You can look up if you know it's a class 1 or class 2, take the plastic section, Z, and of course you should take ZX about the x-axis, and of course the strength of your steel. And even at that, I find that this is very misleading, okay? Because even though it's a class 1 or a class 2 or a class 3, okay, there are a certain length that this element can be unbraced before it still will actually buckle on you. And that's why I find that these equations are very misleading, okay? And I find that, like, unfortunately, even when I went to school, this teacher was stupid enough to always say, well, MR is equal to phi Z Fy, without telling us about the unbraced length of the beam, okay? So, and I will explain to you about what we mean by unbraced length of the beam. And of course, Fy. Now, this here is the best way to go. And hold on a second, this is in the way, okay? Now, I'm going to take my time here, but we are definitely going to come back to this, okay? These are tables called beam selection tables, okay? This is straight out of my handbook, so I copied everything for you so you guys can have a copy of this, okay? Now, let me see if I could, is it clear enough for everybody to see the numbers, or do you want me to try to make it a little bit wider?
It's clear. It's good.
Bigger.
Is that big? Is that better?
Yeah.
Okay. Now, what they've done here, okay, what they've done here is they put down every shape that you can get from a mill. They started with the W shapes, okay. I won't even talk about the W shapes, and I will get into it, okay. And then after they finish with the W shape, they get with the biggest wide flange shapes. In other words, the W's. Instead of the welded wide flange, then we get into the wide flange sections. Okay, so let's get into something a little bit more reasonable. The thing that we would probably end up designing, because even these are very big sections. So that's still very big, I find. Anyways, it makes no difference. Now, so all I want you, so every shape that you have, for example, if you go to ADA and you look at the W shapes that is in the ADA profile, they're exactly the same numbers that you have here. So these are these are the standard designations, and of course, so now one more. Well, let's just do one more. Okay, this is reasonable. So everybody remembers that this stands for the nominal depth, and that's the weight. So here, what they're saying is, I want to stress this, okay? Okay, see here, this is the value of MR. Okay, so MR is equal to phi Z or S, I don't care what it is, right? Fy, okay? So this is the value of MR depending on whether it's a class 1 or class 2 or a class 3. This equation here is the value that you find under this column here, okay? But this value is only good if the unbraced length of your beam is less than 2040 millimeters. Okay, so that means that the compression element of your beam cannot be longer than 2040 millimeters. Now, what does that mean? And this is where a lot of people have difficulty understanding, is that if I have a beam here, okay, if I have a beam like this, and I load it, okay, and of course, this is the compression element. So here, all of a sudden, let's say I have here a span of 8 meters, okay? I have a span of 8 meters. So now, if there's nothing, in other words, in plan view, I'm going to try to do this in plan view so you guys can understand it, okay? So in plan view, here's my beam. It's supported here. It's supported here, okay? And this element here, in other words, the top flange, of course, the top flange is completely in compression, okay? So if there's nothing holding the top flange from moving sideways, okay, it doesn't matter. In other words, if there's nothing laterally supporting the top flange, then in this case here, okay, if there's nothing laterally supporting the top flange, in this case here, the unbraced length of this top flange here, okay, that ends up being 8,000 millimeters. And therefore, if I want to find the MR value that the beam can actually resist, because nothing's really holding that top compression flange in place, well, the MR value is no longer, as they say here, 562 kilonewton meters. I got to go all the way across the table, and all of a sudden, the MR value dropped from 562 all the way down to 123. That's how drastically it reduced its strength, okay? So one of the most important things that you have to worry about when you're designing a beam is all my compression elements in my beam. And of course, if the beam is simply supported, it's very simple. It's always a top flange, okay? All the elements that are in compression in my beam, okay? What is the unbraced length? In other words, what's helping that compression element to stay in place so that I can rely on the fact that it's going to be laterally supported, and therefore I can calculate the value of MR. So what this table tells you is that no matter what shape you have, okay, no matter what shape you have, this is the maximum unbraced length of your compression elements. Okay, not of the beam, of the compression elements. And of course, in the case of a simply supported beam, it would be, it could be the whole length of the beam. Now, let me just clear this so that, okay. So now what happens here is that, for example, I'm going to, okay, let's say I've got a beam. This is my beam here, and it's supported there, and it's supported there, okay? And now I have a span here, again, of 8 meters, okay? But the difference now is I have a steel deck running perpendicular, right? Everybody remember what a steel deck is? Okay. I have a steel deck running perpendicular that is being supported by the beam. That's my steel deck. And on top of that, as you saw, okay, what happens is that at every 2 feet, at every foot, there's going to be a spot weld, okay, that attaches the deck to the beam. Everybody remembers that from the video? So what happens is that in plan view, here's my beam, here's my beam, here's my steel deck, Okay, here's my steel deck. And of course, after that, I've got those spot welds, okay, at every 300. So what's happening now is that because the deck is attached to the beam can no longer, is laterally, it's braced from, it is being laterally braced by the steel deck. And in this case here, because we have the welds at every 300, the unbraced length of the beam here, okay, becomes the unbraced length becomes 300 millimeters because of these spot welds. And therefore, since I'm supporting that top flange at every 300, and it's less than the maximum unbraced length of 2,400, I now can rely on MR being 562 for if this is the beam that I'm choosing. So that's the signal. So if the beam is simply like this, okay, and there's nothing supporting it laterally, and it's got an 8-meter span, well, I've got to go here to calculate the MR. But if I know that I am laterally supporting it, okay, with other elements, it can be steel deck, and there can be other beams, whatever it is, as long as I am supporting it, this is in plan view, as long as I am laterally supporting that beam, or the top flange, I can rely on that to laterally support the top flange, and therefore I can go and rely on this value here. Now, at the first time we do this, this is very, very, very confusing. As we're
Sir,
going to, yes.
sorry to interrupt us. So, for example, if it's supported every three meters, for example, we use the 474.
Exactly. Like, let me
Okay.
give you okay, so very good. Okay, I'm glad you asked the question, Justin. Okay, listen to this. Okay, let's say I've got a beam here, Justin.
Mm-hmm.
Exactly what you're saying. Okay, it's supported here by a column. Okay, whatever. Okay, I'm sorry. It's supported here by a column, supported here by a column. Okay, and then let's say that and this is a girder. Let's say whatever. Okay, I have and there's a beam that gets supported here and another beam that gets supported there. You follow by the girder? Okay.
Yeah.
Well, these beams will provide the lateral for this girder. And if, for example, if this is 3,000 and this here is 3,000 and this here is 3,000, then the L becomes, the unbraced length becomes 3,000, and therefore you're absolutely right, Justin. You would go to 3,000 and that becomes the MR value for your girder.
Yeah.
You follow? So the first thing you have to establish before you come to the table is what is the maximum laterally, what is the maximum unbraced length of my beam or my girder. That's the first thing you should worry about. And like I said, that you see it like from your geometry or your design and all that. So that's the first thing you worry about. And then once you have that value, and you know what your MF value is, then you can come and find an MR value. Okay, guys, I can tell you. Uh, this I was involved in a case. I should talk about this very quickly, but okay, like I was involved in a situation, okay, that uh, one of my colleagues like severely underestimated the loads. Okay, he severely underestimated the loads, and he ended up getting a very small value of MF. Okay, and he didn't realize that the situation of what the unbraced length of that he could have relied on because of what was the beam was supporting. What he did is that he went all the way out here. I don't remember the beam size, but he went all the way out here, okay, because he thought that the beam was not laterally supported. He went all the way out here to get his MR value, okay, and therefore instead of relying on this, he took this value here and he went to choose a beam accordingly. And that's what saved a major catastrophe. One mistake kind of like compensated for the other, okay? And thank God that he made two mistakes that one happened to compensate for the other mistake. The thing didn't collapse, but otherwise, because he severely underestimated the loads, and if you would have taken a really and he would have come and just took this value here, the first winter that building would have collapsed on everybody. So just to let you know that sometimes, Anyways, I know this probably none of you grasp what I just said, but okay. Now, the other thing that you get from this table is that it tells you the B. Okay, so in other words, I have no, I never use the B from this table. Okay, B is that dimension there. Okay, but what's nice about the table, it gives you the IX value. So therefore, when you calculate your IX required for your deflection, you can check to see if it's greater than the IX, the IX provided. And then the other nice thing about here, it also tells you what the VR is for that shape. Okay, so you get your VR value, you get your IX value. I've never used the B from this table. Okay, and of course, the most important thing, it tells you what is the maximum unbraced length. So you see it here. It says that this MR value here is only good if the unbraced length of your compression element is less than these values here. If it's not, then you cannot use these values. You'd have to go here and choose what your MR value is, okay? And you'll see this next week in the lab, what it means to try to calculate the moment resistance of an unbraced beam. And I'll show you that in the lab next week, okay? So don't worry about that. You'll get an overview of what. Does anybody have any questions on this table? Now's the time to ask. Because we'll be using this in the examples, but is there anything that you see here that's not clear? Please feel free to. Oh yeah, and the other guys, just like in wood, you saw that the IX values have a certain scientific notation. Well, in steel, it's 10 to the 6. So whenever you're calculating any type of moment of inertia, make sure that you use it. Otherwise, so this is the other thing I want to stress. So if you remember in wood, it was 10 to the 9th. Well, here in steel, they use 10 to the 6. So whenever you're calculating your moment of inertia, and of course, the units are always, here is definitely millimeters to the 4th. Those are the right units. And of course, here we don't calculate ESI because the E for the steel is a constant. It's assumed to be a constant, and that's why we don't assume, and therefore we only have to calculate the IX because it's bending about the x-axis. Okay, so if there's no questions, I will go on, and like I said, we will come back to this table. Okay, we will come back to this table, and we will use it to, either whatever we want to use it for. So like I said, so what's nice about this table is that it has the class 1, class 2, class 3, all that requirement already built into it. And on top of that, okay, I might as well talk about this now. Hold on, I might as well talk about this now. Now, what's nice about this table is I'll talk about this now and then I'll just repeat it in the lab, okay? What's nice about this table is that this is good for this type of steel. It's good for this type of steel, okay? I know this is the same, this is just the same table, okay? And it's good for this type of steel, the American steel and the American steel, okay? Now, what's happening right now, okay, is that in Canada, they do not roll any more W sections. They're not rolled in Canada anymore, and they're all rolled in the States. So therefore, what's nice about grade 50 here stands for 50 KSI. In other words, 50 kips per square inch, and that's equivalent to about approximately 345 MPa. It's a little bit less, but that's close enough. So even though the Canadian steel used to be stronger, all the values in the table, because they're using a slightly weaker steel, all the values in the table are based on 345 MPa, this grade of steel, okay? And whenever you are going to be specifying the steel for a wide flange, since Canada is no longer rolling wide flanges, you will have to specify ASTM A992, okay? So, and we will be using the ASTM A992 when we're going to be doing the analysis for our girders and all that, okay? So that's something I wanted to, might as well clear up right now. So now, here's a good example, okay? Here's a good example that we're going to start working with so that we can start relating to what we're trying to do, okay? Okay, so we have a W 200 by 31. Okay, so that's going to be the profile. Okay, in other words, the shape of our beam is going to be a W 200 by 31. Now here I'm using some Canadian steel. It makes no difference, but like I said, if you're actually designing, you would have to, this is Canadian steel, but the table is good for all types. The beam has a span of 5 meters. So here, okay, so in other words, there's a support there, and the span here is 5,000 millimeters, okay, or 5 meters, okay. The beam is lightly supported at 1/3 of the span. In other words, it's probably carrying something else that's able to, okay, to laterally support it. So in other words, here, this is 1/3, 1/3, 1/3. So the beam is laterally supported. So in plan view, here's my view, and therefore there's something that comes here and here to laterally support the beam so that it can stay in place, so that we can calculate what the unbraced length is of the compression element. So
Sir.
that's what, yes.
So if it doesn't give us like 1/3, can we assume it's on top of it? Like if they say there's a lateral support, can we assume that like it's from the beginning of the beam till the end, like 5,000 millimeter, for
In other words,
example?
if you're not sure what the lateral support is for your beam, be very
Yeah.
conservative and use an L of 5,000. Yes.
Okay.
In other words, that would be the most conservative thing you can do. Okay. But Omar, is that you that asked me the question?
Yeah.
Yeah, Omar, like what I'm saying is that when you're designing things, you pretty well know if you have any lateral support. You understand? So for example, if I have a, like for example, if I have a beam here or a girder and I have joists that are spaced at every 3 meters, you understand? The joists, because they are attached to the beam, guess what the joists do? They provide lateral support, right? And therefore now, because you have these at every 3 meters, then what would be your unbraced length? 3,000.
3,000. Yeah. Yeah.
Okay, so as long as there's something perpendicular to the beam that can help it stay in its place. In other words, what we're saying, this is the beam. As long as there's something perpendicular to the beam that's going to prevent it from displacing, because this is what happens when things want to buckle. They want to displace. You understand? And therefore, this becomes the unbraced length of the element that wants to buckle. Okay. And therefore, if you have something here that holds into place, well, this is the length that it wants to buckle. And then if I have something here, well, that's the length that it wants to buckle. You follow? So that's what we mean by, if you see what you have that holds your beam laterally in place, then you can, and if you know well, there's ways of calculating, but the resistance required to hold this in place is very, very small. Okay, no, I never even calculated. So as long as I know that there's something there, I know that it will hold this beam in its place. But if I have to, I can calculate it. There's a little formula, but you don't even have to worry about that. As long as I have something that is perpendicular to my beam that can hold it in its place, then whatever that distance is, okay, that's going to become the unbraced length, the LU, unbraced length, okay? So, but Omar, that's a very good point. If you're not sure, be conservative. Take the whole length, take the whole span, and then like my colleague did. He didn't realize that he could have relied on some kind of lateral, you know, bracing, and he took the whole span, and that's what saved him from a major catastrophe. Okay, so here we go. Now calculate the uniform distributed load WF. Okay, so in other words, which the beam can support. Then check the shear resistance of the beam. Okay. Now here, what I'm doing here, this example would be as if you would go, somebody tells you, okay, go to the site. Okay, go to the site and measure up the beam. Okay, and measure up, get the geometry of the beam. In other words, get the span, get what the beam is. Okay, check out what the lateral supports are. Okay, we need to know, for example, if this beam was good enough because sometimes what happens is that, you have areas that were designed, for example, for 2.4 kPa, okay, and then they want to upgrade it to 4.8 because they want to change the occupancy of the room. In other words, they want to make a dance studio now instead of just having a regular whatever it was before. So what's going to happen is that you're going to have to see, well, can this beam actually be upgraded to that new load? And that's what we're going to try to do. We're going to try to calculate the resistance of that beam. Okay. So, okay. And then check the shear. So here we go. Now, okay, my mouse. There we go. Now, so what first thing I said, like I said, the LU provided. In other words, here I'm going to calculate my LU provided. In other words, what is the, excuse me, what is the lateral supports that I can rely on to determine what is the unbraced length of my beam. Okay, I just want to write these down so I don't forget when we go to the table. So we have 1,667 millimeters. Now that I got my LU provided, okay, and I know that it's a W 200 by 31. So that's okay. So what I'm going to do now is, of course, I'm going to go to the beam selection table. Okay, and like I said, it starts from the highest one. I just have to go down until I find the W200. So I'm just going to pan down. Oh, here we go. Okay, W200. So here I'm going to see if I can. So W200 by 31. W200 by 31. Where are you? W200. Oh, here we go. Here's a W200 by 31. Okay. So this is the shape I have. Okay. Now, here's the LU value, the maximum unbraced length that this beam can have in order for me to be allowed to use this MR value of 104. Do I have that?
No, we don't. This is too much. We should
Yes, we do.
Yes, we
go
do.
with.
In other words, you can go up to 1980, and we're only going up to 1667.
Wait. So it's not supposed to be less than 1,066.
No, it has. In other words, what they're saying here, if I want to use this MR value here, right here, okay, the LU value has to be less than this value here. Is my
Oh,
L?
okay.
So everybody understands that? Okay. So since I have 1,667, and which is less than this maximum LU value, therefore I can have an MR value of 104. Is that getting a little clearer? Don't worry, we'll do more examples, but is everybody getting a little clearer how this works? Okay. So therefore I know that I can base myself that the MR value is 104 kilonewton meter. Okay. Like I said, here's the units for what's in the table. So from the table, since the maximum unbraced length is 1,980, and what I'm providing is less than the maximum, okay? Therefore, I can take the MR value that's in the first column, okay? Now, I know that my design objective is that the MR value has to always be greater than or equal to the MF value, okay? Now, let's assume that this beam is going to be loaded, right, like a uniformly distributed load. We know that the MF value, if it is going to be a uniformly distributed load, and this is something of course, you're going to have to, okay. So we know that the WF value is equal to the span divided by 8, and therefore we know that the maximum factored load that this beam can carry should be the MR times 8 divided by the span squared, okay. So all I'm doing is I'm isolating WF, and of course, Now I get WF has to be less than or equal to 104 kilonewton meter, okay? And therefore the WF value ends up being 33.28 kilonewton meter. So that is the maximum load, factored load as a matter of fact, that this beam would be able to carry, okay? Now, does anybody have any questions? All
It's
good so
clear.
far? Yes?
Yeah, it's
All
good.
good? Okay, great. I want you guys to digest this because I don't want to rush. I mean, like, this is the first example. Now, in real life, I would know how much my dead load is, and then I can actually calculate my live load. But since I don't know here, I'm just using this as an example, okay? I'm going to say, oh yeah, the VF value, okay, is equal to WFL over 2. And of course, I just calculated what the maximum shear that this beam can carry, okay? And therefore, the VF value would be 83.2, okay? Now, from the table, okay, the VR value was equal to 275. And I should have shown you that before, okay, because usually when I come to this table, okay, this was the W200 by 31, okay. Here is the, okay, so here are all the VR values. It was a W231. So here is the VR value. In other words, the maximum shear resistance that this beam has is 275. And of course, the IX value I don't need right now, okay? So here is where I can get my IX value, my VR value, once I come to the table. Okay, so let me go back to here. Now, all of a sudden, I take the value of VR, okay, and I multiply it by 0.08. So I take the value of VR in the table, I multiply it by 0.08, and I end up getting a VR value of 220, which is still okay, because it's still greater than 82, 83.2. But why do you think I want to multiply this value by 0.08? In other words, why do I only want to take 80% of the shear resistance that this shape has? Does anybody have an idea, or does anybody want to venture a guess? And trust me, all guesses are good. There's nothing wrong with a bad guess. There's no bad guesses or incorrect guesses.
To be more conservative or more like cautious?
You're being more conservative, and there's a reason. I like to know the reason.
For safety?
For safety, okay. I know that you guys right now, Nermin, if you don't mind, yeah, thank you, because I don't know if the rest of you heard. Okay, now guys, I don't, I'm going to talk about this right now, but you have to remember, okay, when I have a beam, this I'm drawing an elevation here. Here's the flanges, okay, okay, and here's the flanges, okay, and here's my column. And of course, I'm not going to draw the column on the other side, okay? Normally, when we want to connect the beam to the column, okay, we're going to have to do something. Are we going to be welding? Are we going to be bolting? Okay. So if we know we're going to be welding, we don't have to worry about nothing. Why? Because welds do not reduce the area of the, oh yeah, first of all, let me tell you something, okay? I should have told you this in the beginning, but I don't know if they talk about this in your physics class, okay? But the MR value or the MR value that you calculate, that comes from this element and that element only. Okay, so in other words, it's a top and bottom flange that provide the MR value, okay? And the VR value is provided by the web. Okay, so the web is what contributes to about 95% of the shear resistance is the web. Okay, 90, and we rely totally on the web for the shear resistance. And of course, the MR values are the flanges. So the thicker the flanges are, the more far apart they are, the bigger the MR value. The thicker the web is, the longer the web is, the bigger the VR value. So the top and bottom plates is what gives you the MR for a beam, and the web is what gives you the VR. So basically, if I'm going to be welding, not a problem, because welding does not remove any material. But if ever I'm going to be bolting this beam, in other words, be making holes here, okay? If ever I'm going to be bolting, I have to make holes in this web here. So what's going to happen is I'm going to be removing some material here. Okay, I'm going to be removing material. And therefore, the area of this web is no longer a full web. And therefore, to allow for the possibility that in the future, okay, I'm going to have to make holes in the web to connect it to the beam, well, I'll only take 80% of the VR value in the table. So it's just to kind of assure myself that somewhere down the road, okay, if and when this beam will be detailed so that it's bolted, or I have to make holes to put bolts through it in order for it to be connected to the column, okay, then to compensate for that little loss of area that the holes are going to make, okay, I will reduce my VR value. In other words, the VR value is from here to here. But then if I want to calculate the VR value through the bolt holes, it's much less because I have less steel, and therefore I'm guesstimating at this point. So I will take only 80%, and I'll say that I'll consume 20% for the bolt holes. And that's why we always take 80% of the value in the table, so that in the eventuality that we do make holes in here, we're still safe, okay? And that's the reason why we use 0.8, okay? It's just a good allowance for future fabrication of the connection. Is everybody clear on that?
Yeah.
Yeah.
Okay.
Yeah, it's clear. I just have one question.
Yeah, go ahead.
So when you put the bolt in these holes, you basically they have a VR too, right? Each one of them.
Omar, don't jump to class number 8 or number 9.
I'm
We
just
will,
asking because
we will be going through the whole thing, like the VR for the bolts, the VR for the holes, the bearing, and we'll do the whole thing. We are going to do that in this course. So I
okay,
don't want to confuse everybody, but you will learn all of that.
okay, just making sure because like it doesn't get lost. Like I mean, I know you drill a hole in the surface, but at the end you're filling the hole with the bolt, which is
On the and when we get to connections, what you're saying is not correct.
okay. I don't
Okay.
know. I'm just
And I will
clarifying.
explain to you all of that when we do the connections. But you see, you're you're not replacing the material. The material of the web is not there. And then I don't want to confuse everybody. Let's just stick to beams, and then when we get into connections, Omar, bring it up again, and I will be more than happy to go into more detail and explain to you why the material doesn't get replaced. Okay.
But isn't there other like ways to connect the beam to the column, like
Oh
not
yeah.
uh,
There's a number
setting
of ways.
holes in the web?
Yes, there is. In other words, you can there's all types of connections, but the most typical one, Norman, is and you'll see that when we do connections, is that you weld the connection to the column. You
Huh?
make holes here that in the connection. Like in other words, it's called a double angle connection. You weld it to the column, and then you make holes in these things that you're going to weld to the column. It's got nothing to do with this. And then after that, you make holes in the beam so that you can put the bolts through it. And this is the most typical connection that you do from beam to column. You understand?
Yeah.
Yeah,
Okay.
so in other words, that is one of the most typical connections that you have. It's the one that everybody designs, it's everybody, okay? So therefore, that's why, in a way, since this is one of the most typical connections, that's why you try to make an allowance for the possibility that in the future you will make holes. If you're guaranteed that you're not going to be connecting it, if you know that you're not going to be connecting it with holes in the web to pass bolts through it, then you don't have to reduce it to 80%. You can rely on the total VR. But at this point here, look, Norman, even if I reduce it by 80%, look at this. Do I have any problem? This is just so you don't, like, for example, if all of a sudden my VR value was 220 and then my VF value was 225, well, when it comes to the bolts, I better do my connection right away to see if I'm going to have a problem. So that's all that is. Okay, so let's not jump 8-9 lectures away. Let's just worry about designing the beams, and then we'll worry about designing the connections for the beams. Okay, but we will be doing that. Now, this, like I was saying, assume that the live load, this is just me giving you some kind of value. Assume that the live load is 3 times greater than the dead load. Okay, calculate the deflection of the beam due to the dead load and the deflection of the beam due to the live load. Now, I have to give you this ratio, but in real life, you would calculate the dead load, excuse me, and then you'd be able to calculate the live load accordingly. But I'm just giving you this ratio so that you guys can do some, mathematical. So here, all I'm saying is that WF, of course, this is the load combination number 2, where I get 1.25 times my dead load and 1.5 times my live load. And I'm telling you the live load is 3 times the dead load. I'm just giving you a ratio. It can be 2.5, it can be 2, it can be 1 in real life, but you're going to have some kind of ratio because you'll know what your live load is, you'll know what your dead load is, and so on. Okay, so here, all I'm saying is that WF, of course, I replace the L by 3D, and I say WF is equal to 0.57 D, and therefore D is equal to WF divided by that, and I end up getting that my dead load ends up being 5.8 kilonewton per meter. And of course, if that's my dead load, my live load would be 3 times that value. Okay, and therefore, so here's the live load that I have on the beam, and here's the dead load. Now, in steel, okay, in steel, we want to different, be able to, do different things with the dead loads and the live loads. But here we go. Okay, so now, if you remember, okay, this is how you calculate deflection. Okay, deflection, if you go to your beam formulas, okay, this is the formula to calculate deflection. In other words, if you go to the beam formulas, you're going to have 5W L to the 4th over 3. You won't see these subscripts here. That's the only difference. But this, to me, the reason why I put a D here is because this is the deflection caused by the dead load. Okay. So here, this is in other words, if I have something that is simply supported and I have a uniformly distributed load across it, okay, this is W, and I have a span here L, okay, this is the equation to calculate the maximum deflection that is going to occur at the middle of this beam. And that you get from your beam formulas. Like of course, I've been using this like constantly for 40 years. So I know like this one like the back of my hand, but you guys, I don't expect anybody to memorize this, but if this is the equation for deflection. Okay, so now I know that 5, this was a dead load I calculated. Okay, fair enough. And here's my span. And then now here, guys, what's nice about kilonewtons per meter, okay, what's nice about kilonewtons per meter is that it's the same as saying newtons per millimeter. So there's nothing you need to do there. You can just put newtons per millimeter is the same thing like a kilonewton per meter. And of course, you put your span here in meters, so in millimeters, not meters, so you get millimeters squared. And the reason why you do this is you want to make sure that this cancels this. You want to make sure that that cancels that. You want to make sure that that cancels that, and you end up with millimeters. And that's why. So this is very important that you put this in millimeters so that if you don't want to change, oh yeah, this here, you must have covered this in your physics class, okay? The modular elasticity of structural steel, they must have told you it was about 200,000. Did you guys cover this in physics? MPA?
Yeah, we
Okay.
did.
Okay. So in other words, this is a metric or an imperial. They either told you it was 29,000 an imperial, 29,000 KSI, or 29 million PSI. I don't know what they told you, but this is imperial. We're not going to be doing anything in imperial. So therefore, this is the, and guys, this is an assumed value. Okay, it's not an exact value. It's just a reasonable value for all structural steel. Okay, so this is your E steel. Okay, so here you go. Now, I'm going to calculate the deflection here, okay, and end up getting 7.5 millimeters. Why do I want to calculate the dead load deflection? Why do I care about that? So does everybody understand what I'm doing, right?
Yeah, but I don't know why you're doing it.
Okay, so like, okay, so here we go. Let's change colors. I like changing colors. Okay, so this is my beam, right? And let's change colors again. And so what we're saying here, I'm going to greatly amplify it. Well, I mean, I should have made it a little bit more accurate. Okay, so here's a deflection of 7.5 millimeters, but that's only under the dead load. In other words, here, the load that I'm applying to this beam is only the dead load, WD. So why do I care about the dead load deflection? Because once you put the dead loads and I attach the materials to them, right? It's not going to be contributing to any more deflection. It's already going to have deflected under itself, weight and all the dead load or the superimposed dead loads. So it's not going to be affecting any materials that are going to be attached to it. So why should I care about the dead load deflection?
Still no idea.
Okay, I just thought I'd throw that out there, see if anybody had any reason why we would want to worry about the dead load deflection.
To see if the deflection that will caused by the life load and the dead load are within the limit.
Oh, like what I'm saying is that normally when you're worrying about deflections that might affect the materials that are being carried by by your member, you're always worried about the deflection being caused by the live loads, because those aren't there when the materials, they might not all be there when you're installing the materials, and then one day maybe you'll get the whole floor is going to be loaded with people or whatever, and then all of a sudden it's going to deflect under that load that you designed it for, and then the material that's attached to your structure can start cracking. Your floor tiles can start cracking, or your ceiling underneath can start cracking. So that's for deflection for under service loads, in other words, under your live load. Now, the reason why we calculate the dead load deflection, guys, okay, is that if ever, okay, let's say that your client does not want to see a sag in his floor, okay? In other words, when nobody's standing on the floor, he doesn't want to see it kind of like, I mean, you won't see this, you won't see this. Or let's say that under dead loads, the equipment is so sensitive, you want the floor to stay straight. So you're going to calculate, this is delta D, okay, delta D. So this is your deflection under dead load. So what you're going to do is you're going to tell the people that are fabricating the beams, okay, you're going to tell the people that are fabricating the beams to camber the beam. Camber beam means that you want to have it deflect upwards by 7.5 millimeters. So this is called a camber. In other words, what they'll do, that they will actually arc the beam by 7.5 millimeters, okay? And if you guys want to know how this is done, just go to YouTube, okay? So it's what they do is they actually load the beam past its elastic limit, and this is all calculated, and they know how much more load to put so that they can create a permanent deformation in the beam. And therefore, when this beam gets installed with the camber up, and then when the dead loads get imposed on them, okay, then the beam becomes straight. Okay, so to compensate for that sagging that it's going to have under its self-weight and all the material that it's carrying, we will camber the beam, okay, upwards. So this way, when you put all the loads, instead of having it like slightly dipping, it's going to become nice and straight. And that's called a camber. Okay?
Sir,
Yes.
let's say it's more than 7.5 millimeters, like a little bit more. Does that will
It,
affect, like, it's gonna like kind of ruin the the steel? I'm just saying, like, if it's like a huge number and you're trying to just like do this process, is that gonna like ruin the material or no? I'm just curious.
it will not ruin the material. Like it does not ruin the material. Like Omar, you can camber up to 4 inches, 5 inches. In other words, 100 millimeters, 150 millimeters. Okay, and where the camber becomes very important. I'll tell you where it becomes very important. That you should do it so that you don't, excuse me, that you don't create another problem. And uh, but the camber will not ruin the material. Steel is steel. The only thing that ruins steel, Omar, guess what it is?
Rust.
Exactly. Okay. So in other words, it's that's the only thing that's going to ruin the steel. So in other words, when they make this camber in the material, okay, it's just has a permanent deformation imposed in it, and then after that, as you put the load, it comes back straight. Now, let me give you an example, okay, where this becomes very important. Okay. And I can tell you that I know this for a fact because I was involved in this file. Okay. So here is, okay, here is a typical bay of a shopping center. Okay. Now, I don't know what this is in meters, but I can tell you what this is in feet. This was 40 feet by 40 feet. Okay. I don't know if you guys can appreciate, but 40 feet starts becoming an appreciable span. It's like almost what 13 meters, right?
Yes.
And what they had here is they had girders here. They had a girder there, and at 1/3 they had a beam. They had a beam. Okay. Then this, of course, becomes a beam. So this is the typical layout. In other words, this is okay. So you had a girder here, a beam, and a beam here. Okay. And what happened was is that this is your steel. Okay, this was a steel deck. Okay, a steel deck, and of course, and this is your girder. It was a steel deck over this, and of course, the engineer designed it as a composite section. So you had Nelson studs all over here, Nelson studs. Okay, and all that. And he didn't bother cambering the beams. Okay, when they poured the concrete on top of here, okay, the center here sagged by 5 inches. There was a 5-inch, in other words, there was 5 inches more concrete than was supposed to be there. And everybody was so concerned that now the structure did not have the carrying capacity because they put more concrete than was initially thought of. That's how, and that caused a big to-do, okay? And we had to go through so many things to prove to the guy that, okay? So here, in this situation here, they could have easily cambered this by 5 inches, okay? So that by the time they would have put the concrete down, okay, it would have all been nice and straight. So instead of ending up with a straight slab on top and all these things sagging underneath, mind you, it doesn't matter because there was a suspended ceiling, but this is a perfect situation where cambering should have been done for both the beams and the girders. Okay. So that's, like when you have that situation, you want, and by cambering, it does not ruin the material. It just creates a permanent deformation. Then when the load comes in, it goes back to a straight level. And if you do this correctly, I can tell you that, I mean, like even though this is assumed, and this here is, also depending on, okay, it's within a millimeter. Trust me. Okay. I mean, I've done some deflection calculations where I did a calculation and I said the deflection should have been like 7 point something, 7.2 millimeters, and then the actual measured deflection was about 7.5 millimeters. So these calculations are fairly accurate, even though that's assumed, and this could be slightly off because the piece wasn't milled perfectly because of the tolerances. So there you go. There's a perfect example where cambering would have been understand. Or you can have, for example, you're in a you're in a very sophisticated lab where the equipment can take very little very little distortion or deflection, whatever, for whatever reason. All I'm saying is that if you need to have if you want to have straight floors, okay, if you want to have straight floors, then you calculate the deflection under dead loads for steel, and then you camber the beam to that amount. You specify on your drawing, camber, and you give them the amount that, and the guy's going to artificially, you know, arch this beam in the other direction so that when it actually gets installed, you end up getting a nice straight beam after all the dead loads are being placed in the building.
Okay, I understand completely. Like it's legit. But a quick question
Yes.
on the points of connections on either side of the beam. What would happen to them if you
Well,
like?
if I have a column here and I have a column here, is that what you're
Yeah,
saying?
exactly,
Well,
exactly.
yeah, exactly. Here the deflection is zero because these things don't move here. The only thing, like, it's zero. It goes like this. Your deflection. You understand? Because these things don't move. They're resisted by the column. Okay.
You know what I mean? Like when you put the weight, like like you have 5 inches. Uh,
Of additional concrete. Yeah.
y no, the opposite. Like when you said they do this, what's it called? Cambering.
Cambering. Yeah.
So yeah, so when you do it, when you put the connections, you basically like you kind of the columns came closer to each other, but when you put the weight, they're starting to go far away to straighten up
Oh,
the column.
you mean what's going to happen to these columns here when the thing goes back
Yeah,
straight?
exactly.
It is so small that it probably taken up in the tolerances that you have in the holes here. You understand? Because these holes are about 2 millimeters bigger than the actual bolt size. So by the time this thing pushes out, it'll probably all be taken up right here in your bolt holes.
Okay, makes sense.
It makes sense, you see? So, but very good point, Omar. Okay, but you understand, like, let's not get into connections, but you'll see that these bolt holes are 2 millimeters bigger than the bolt size themselves, and therefore they can easily be taken up there. Because if you actually do the calculation of that deflection versus, you understand, it's very small, the lateral displacement. Okay, but good point. Okay. Okay, so that's why we calculate the dead load deflection. So if ever you want to camber your beams and have a straight floor, you just use the dead load. And of course, you want to calculate the live load deflection. Okay, so therefore we would take the live load. Okay, and now all of a sudden I would calculate the deflection on the live load. I would use the same formula. The only difference that here I would replace this by WL, just the live load. And remember, when we're doing deflections, you do not factor the loads. You do not use the design loads. That's only for strength. For serviceability, you always use the specified loads. And therefore, I do this calculation and I end up with 22.5 millimeters. Okay. Now, all depending on your floor, what it's carrying. Okay. Now, determine if the deflection due to live load meets the requirements of a member supporting finishes susceptible to cracking. Okay, so whenever you have materials susceptible to cracking, in other words, you can have a floor tile that's susceptible to cracking, you can have gypsum that's susceptible to cracking, whatever material that being supported by your floor, by your structure, if it's susceptible to cracking, your deflection should stay maximum. Okay, maximum deflection should be L over 360. Okay, keep that in mind. That's what's recommended in the National Building Code. That's the minimum requirement. If you guys want to make it higher, but don't make it lower than L over 360. What I mean by L over 360, like lower, make this L over 240. That's a lower, in other words. Okay, so that's the maximum deflection. So if I do this, I do L over 360, I have a span of 5,000. The maximum deflection would be 13.9. The deflection I already have, therefore, guess what? If ever this beam was in place and all of a sudden it needed to support something that was susceptible to cracking, because of serviceability, it would be no good. Then, of course, that would also limit you what you can do with the floor. Does anybody have any questions?
No.
Easy enough?
So I have
How
a
are we
quick
doing
question.
time-wise? So good? Okay, so guys, that is, okay, that's like, finding the resistance of a member and then, doing whatever you want to do. So in other words, that is, just like we did in concrete, we calculated the resistance of the beam and then we went back to check if it was okay. Same thing we do in steel and anything, okay? Now,
Sarah, I have a quick question. So
yes,
since the floor is susceptible to cracking,
yeah.
for example, or if we already built the structure, what floor can we put so that it doesn't crack? Can we put like a wood floor or something, or
No, you just take away the materials that are susceptible to cracking.
okay?
In other words, not a question of whether you put a wood floor or not. The question is that if my floor is going to have, like, in other words, okay, so that you guys can appreciate what we're doing, okay? Let's say that this is the floor, okay? Here's the floor, and okay, here's the beam, okay? The floor is already built here, okay? The floor is already built, but it's only got a sheet of plywood on it. In other words, there's nothing there that plywood is not susceptible to cracking. You understand? There's only a sheet of plywood or whatever, okay? Now, the guys buy this building. Okay, this was an old industrial building and there's only a sheet of plywood there. Now, the guy buys this building and all of a sudden he wants to turn it into a loft. In other words, he wants to, make an apartment out of it. And then he says, well, I'm planning to, put some gypsum on the underside here so I can have some, finished ceiling. I want to put some ceramics here on the floor so I can have a ceramic floor in the loft, and I can have, the apartment below is going to have, a finished ceiling and all that. And all of a sudden he says, can I do it? And you're going to say, well, no. Do you understand what I'm saying?
Yeah, I get it. Thanks.
Okay, so in other words, that's another reason why you have to be able to calculate deflection, because if all of a sudden the thing gets transformed from a warehouse or I don't know, like a storage area, and they want to make a room out of it, and all of a sudden they want to start putting materials that are going to be susceptible to cracking, well, then you have to check the deflection, and once you check the deflection, if it doesn't stay within these limits here, then you cannot, just leave things the way they are. Okay, now I don't want to confuse you. And then you can go and improve the moment of inertia of that beam if you need to, okay? But you can't just leave like that. The answer would be no. That means you have to go further, okay?
Thank you.
You're welcome.
Yes, sir.
Yes.
Like it's not good. What would you do afterwards?
Well,
What-
like just worry, like I'm only going to confuse you, okay? So just leave
Can we
it.
not?
I'll
Can we
do
not
it.
use?
Yeah, go ahead.
Can we not use the 13.9 millimeters and put it back in the formula, the deflection formula, to have the new live load and dead load, and use that?
Well,
Get
no,
it?
like now the next example is that's what we're going to be doing. In other words,
Okay,
here what I'm saying, Justin, what I'm saying here, Justin, is this beam is already in place. It's as if
Yeah.
like it's there, and all of a sudden they want to do a transformation to the structure, and they want
Okay,
to,
okay.
you know what I'm saying? And therefore, you have to live with these constraints, okay? And
Yeah.
then you're doing the verification to see if the guy wants to, like the architect says, hey, we're going to be putting these nice big ceramic tiles on the floor. We're going to be finishing the ceiling. They're going to come up to you and they say, is that going to be a problem? And you're going to say, well, let me check. And you do your check. Say, yeah, there's going to be a problem if we don't do anything.
Mhm.
Then there's always something that can be done. Understand? But you cannot just say, yes, go ahead and do it without modifying something, because your calculation telling you that no, you cannot do it. That's what this is saying.
Yeah, okay. Thank you very much.
Okay, you're welcome. Okay, so guys, now like I said, this is looking at it from one point of view, and then after that, I'll show you how to design. Okay, now okay, so now here. Determine the lightest wide flange section beam. Okay, the reason why I say the lightest is because in steel, you can always, you should always try to find the lightest shape. In other words, the one that weighs less per kilogram per meter that can satisfy all your design requirements, okay? Determine the lightest wide flange beam that is simply supported with a span of 10 meters, which carries a dead load of 2.2 kPa, which is pretty heavy, right? And this includes the self-weight of the beam, because I didn't want you guys, okay? And a live load of 4.8 kPa. So in other words, here I got a good, nice concrete floor, and it's got a good live load of 100 pounds per square foot. Now, the tributary width of the beam is 4.2 meters. Now, of course, if you have your own geometry, you can determine that yourself, but you need to know the tributary width that the beam is carrying, okay? The live load deflection is limited to L over 240. Well, that's good. In other words, here I don't have anything that's that's going to be susceptible to cracking, so I'm going to try to limit it to L over 240. And if I was doing a floor, I would probably bring it up to L over 360. Okay. Now, the beam is laterally supported at every 300 millimeters by the steel deck. So what this means is that because the steel deck is going to be spot welded or screwed at every 300 millimeters, that is going to be able to provide the lateral support to the beam, and therefore the unbraced length of my beam now is 300, okay? Now, and of course, the steel here makes no difference. The table is good for that steel. So what I do is I start by determining, okay, which load combination is going to govern. So case number one, always 1.4 times my dead load. And case number two, 1.25 times my dead load, and 1.5, and therefore I have 9.95. And of course, case number two governs over case number one. I should call load combination one and load combination two. And this becomes, of course, my design load. Now, I want to convert this, okay, into a uniformly distributed load, and therefore I take my factor load and multiply it by my tributary width. Everybody remembers that. In other words, here's my beam, okay? I want to take all the load and carry it there, put it there. I want to take all the load and I want to put it there, and therefore this is my tributary width. And that's what allows me to sort of consider it to be a uniformly distributed load right across the beam, okay? So that's what that means. And of course, now I have 9.95 times 4.2. I end up with 71.79. I don't know why I left it like that. I normally, if I was doing this in real practice, I would just put 41.8 or maybe even 42. I really don't understand. I don't know why I left it to decimal places. Okay, so here is my WF. Now, what else do I need to know? Well, since I have some deflection criteria, I need to be able to calculate my WL. Now, of course, the WL is the specified load times the tributary width unfactored. So I have 4.8 kilonewtons per meter times 4.2 meters, and that gives me the WL, the uniformly distributed live load that the beam is going to be carrying, and that's for serviceability. Now, I'm ready to do some analysis. I know that since it's simply supported, WFL squared gives me my MF, and I end up with 522.4 kilonewton meter, okay? And of course here, everything's in meters. And of course my VF for a simply supported beam, WFL over 2, and this is my shear, okay? Now, what I need to calculate is from my WL, what is the moment of inertia required, okay? So WL in this case, I said was L over 240 instead of L over 360, okay? That's, I'm just giving you this as, in real life, if this was a floor, I would put 360 here instead of 240. And this is the dead load, I'm sorry, this is the deflection, the maximum deflection at the center of a simply supported beam. And therefore, I'll put this in terms of IX required. Now, why do I put IX here, guys, in steel? Does anybody have an idea?
To not confuse the two with the wood structures, maybe.
Oh, sorry?
To not confuse the steel with the wood formula. I don't know.
Okay, no, it's got nothing to do with the wood or the steel because you're doing steel, but I hope you guys appreciate, I don't know if they talked about this, but you understand, this is my white flange, okay? This is my white flange. And basically when you're talking about a white flange, this is one axis of the white flange, and this is another axis of the white flange. Everybody sees that? Okay. And in steel, this is called the strong axis. This is the x axis, and therefore the moment of inertia will be calculated with respect to this axis. That is Ix. In other words, the moment of inertia of this section is calculated with respect to that axis. And then you have Iy. And the moment of inertia is calculated with respect to this axis. And of course, Iy is much weaker than Ix, okay? So you, like whenever you're going to be so whenever we say Ix, it's the moment of inertia of the beam with respect to the x-axis, okay? And the moment of inertia of this section is all calculated with respect to that axis. And the moment of inertia Iy is all calculated with respect to that axis, okay? So just keep that in mind, okay? And if you're going to use Ix, you better make sure your beam is actually bending about the strong axis. In other words, when this beam is being placed in place, okay, here's my x-axis, make sure it's bending about that axis. Otherwise, your calculation is totally wrong. As a matter of fact, I've seen that. Okay, guys for some reason had turned the beam and put the x-axis in one direction, and then they calculated deflection, and it was totally wrong. So keep that in mind. In steel, they will always refer to the principle, to the axes of the section, either the strong axis, which is referred to the x-axis, or the weak axis, which is referred to the, so this is the x-axis, and this is the y-axis, okay? And in the tables, you, as a matter of fact, you always see Ix or Iy and so on. Okay, so now the Ix required, so I calculate 240, 5 WL, which I calculated before of this, okay? And of course, E is 200,000 MPa. That's the assumed value for the modularicity. And therefore, if I do this calculation correctly, like I said, the only thing you have to be careful about here, this kilonewtons per meter is the same as newtons per millimeter. So if you happen not to convert anything there, it won't hurt you. But this is where you have to make sure that you're working in meters, okay? Now, you notice that I went to a cube here because this L canceled that L to a cube, okay? That's why I went to a cube here, okay? And of course, the 240 went up on top here, and that's where I got the 240, okay? So I'm just isolating the Ix. So that's the, so therefore the Ix required is 315 times 10 to the 6th. And you notice I use the scientific notation 10 to the 6th because all the tables in steel are prepared for the moment of inertia 10 to the 6th. So now that I've got, okay, now, before I rush to the tables, okay, I know that I have, okay, I have my MF value, so I can go to find an MR value, okay? I don't care about this right now. I'm going to check that after once I choose my section, and I have my Ix required, okay? So before I rush to the tables, one of the first thing I have to worry about is what is my LU provided? In other words, what is it that I have? And I know that in this case, my beam is here, and that the steel deck is laterally supporting the beam, the top flange of this beam at every 300 millimeters, and therefore I know that in this case here, my LU is equal to 300. Okay, the LU provided, and that should be the less than the LU that I have in the table. So So now I have a 300 millimeter, okay, because that's the steel deck is going to provide that lateral support to the top flange that's in compression. Now that I got this value, I can go to the table and try to find a member. So let me write this down so I know what we're looking for. So I have an MF equal to 5224 and an IX equal to 315. And I'm not going to worry about the VF because we'll come back and check it. Okay, so now we come to the tables. Okay, and I want to explain something further about these tables. Okay, so guys, here we go. So what I like to do when I come to these tables, okay, I want you to notice something here, okay? I want you to notice, okay, I'm gonna talk about it here. So I'm looking for an MR value that's at least 522. So I like to go through these tables and look at the MR value here until I find 522. Do I find any here? No. That means that none of these sections would be able to provide me the resistance that I'm looking for. I keep going up the MR value here, 20, I'm sorry. Okay, so here we go. So I'm looking for at least, oh, here we go. I have here, okay, 522. Everybody sees that?
Yeah.
Okay, so right away, at least I have an MR value that is greater than, oh, okay, it's almost greater than or equal to. And look at this, the LU has to be 3076, great, okay? Now, why, what they're showing you here, and I want you to realize this, when I say pick the lightest section, okay? What they're showing you here, that out of all these sections that you have here, all these shapes, okay? The one in bold is the one that gives you the highest resisting moment at the least amount of weight, or at least the same amount of weight. You understand? So if ever I come here and I have this, okay, and if for some reason I have no problem how high or how deep my beam is, instead of me taking this section here, I might as well go to the top where the bolt is and take this section here, because this can only weigh 74 kilograms per meter as opposed to 91 kilograms per meter. So you're going to be saving 20 kilograms per meter just by choosing that section. So when I say choose the lightest section, I want you to always find where the bold numbers, okay, are probably going to be the ones that you're going to choose from, okay? So here, instead of choosing this, which would be good, or this, instead I would go up and I would choose the one that's in bold that would give me, okay? Now, I found my MR value. I check my LU. Oh, I can go up to 2040. I know I have 300, so I have no problems there. Therefore, I can use this value here. And then at the same time, while I'm in the table, I get my IX value and I get my VR value. How are we doing time-wise? Oh, okay. Fair enough. So there you go. So now, so that's what I'm gonna, okay, so clear all drawings. So from the table, I take a 5W by, okay, by 74. I know the LU of 2,400 is greater than the LU is greater than the LU provided, so I can use the MR value that's in the first column. So I have an MR value of 562, which is greater than 525.4. Great. I have a VR value. Like I said, I will take 80% of that value, the VR value from the table, okay? Because in case I need to make holes or whatever, I have 824 is greater than my VF value of 209, perfect. And my IX provided of 411 is greater than 315. Therefore, this thing, the deflection will stay way below L over 360. And therefore, in terms of serviceability, perfect. I've decided, just like we did in wood, we satisfied the strength requirement, we satisfied the serviceability requirement, and that means that this beam will be very adequate for the span, the way it's being laterally supported, and for the loads that it's carrying to safely carry those loads and adequately, perform in service when people are going to start walking all over it.
Sir,
Yes.
I have a question.
Okay.
It's kind of okay. That's the beam you chose. would it be cheaper in real life than the other one, or
Which one?
like now you chose the 74, right? From the 91.
But yeah, because look, steel is sold by weight.
Yeah, exactly. So that's what
Okay,
I figured.
this weighs 91 kilograms per meter. This one weighs 74 kilograms per meter. Which one is lighter?
The 74, of course.
So therefore, that one would be cheaper.
Okay. Okay.
See, because when they're rolling these things, Omar, okay, it's all machinery. It's just the amount of material that's being used to make the shape that's you're paying for. You understand? Now, are you, like are you asking me, for example, in in reinforcing steel, okay, to make a number 10 bar or a number 35 bar for the fabricator, it's the same thing. Do you follow? The guy that's going to be the mills I'm talking about, but the guy that's going to be placing it might charge you more for the 10M bar than a 35 bar because he needs more time to place more bars. Okay, but in steel, where the guy puts one beam, a W500 by 74 or a W410 360 by 91, the time it takes him to erect that beam is going to be basically the same. So it's not going to change the price for erection. It's not going to change the price for fabrication. It's not going to, understand? So therefore, when it comes to steel, it's almost everything is based on pounds per pound or kilograms per kilogram. Okay. Fair enough. And what I'm saying, what I want you to realize is these tables, what I like about these tables, that, so for example, Omar, let's say the architect is going to force me into a space that's only 380 millimeters high. Understand? Then I won't have a choice than to take this one here. You understand?
Yeah, I see. Okay.
And so that's where, you know, so if you don't have any geometric constraints on, you know, like how far your beam can go down, like take the one that's always on bold, because that's going to give you what I tend to use the term, the best bang for your buck. Understand? So for 74 kilograms, and look at this one, okay? Omar, I want you to see something here, okay? This is 74, and this is 74. In terms of weight, does it make a difference?
No.
So in other words, whether I buy this or this. Now, the nice thing about the new handbook, if you guys ever buy the new handbook, they also highlight in yellow. I don't have the new handbook. They also highlight in yellow what are more available by the mills. So they already give you an idea of which ones you should be going for based even on availability, if availability becomes an issue, okay? But here, this is 74, this is 74. In other words, in terms of cost, would there be a difference?
Not really.
Okay, but so why would I still want to go with this one if this one's going to cost me the same thing?
Because it has a less MR.
The
Like
LU
it's
is
less
too
than
small.
the required.
It
I have
has,
also five
okay,
small.
that's number one. But let's say that let's say that okay, let me okay, not for this example, but let's say my MF was 510. Okay, let's say that was my MF, and I saw that this was good. You follow? Let's say, okay, I'm just hypothetically saying. Now, the reason why, if I don't have a constraint on how deep the beam has to be in order for it to be in place, well, instead of me taking this one, even though these two weigh the same, look at the moment of inertia here and look at the moment of inertia here. Look at the VR here. So therefore, I get a stiffer beam, I get a better shear resistance and everything, and I get a higher MR value, and I'm paying the same price for the beam. So that's why, you know, like they suggest that if you happen to fall in here for a beam, okay, well, if you don't have any constraints, go up to where it's bold and choose that one, because you're going to be getting better values than, you know, you actually need. That's all they're saying, this table, okay? So now, oh, mouse. And I think, okay, so I think I'm going to, like, there's an assignment that's going to be coming in soon. I think I scheduled it for 9:45. So it's 9:36. Oh, wow. I like to finish by 9:40. So I'm 4 minutes earlier than I planned to be, okay? So by 9:45, guys, like I said, okay, and that's it for the lecture. So I'm going to pause this. Hold on, so I'm going to pause the, going to